What's up, algebros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, today we're going to talk about linearly independent sets and bases again. So let's go ahead and talk about, we got some definitions to start off with. An indexed set of vectors, v sub 1, v sub 2, so on and so forth to v sub p, in a vector space capital V is said to be linearly independent if the vector equation c sub 1 times vector v sub 1 plus c sub 2 times vector v sub 2 plus so on and so forth plus c sub p times vector v sub p equals the zero vector has only the trivial solutions where the constants c sub 1, c sub 2, so on and so forth to c sub p all have to be the zero constant. And just to be clear, these v's are vectors, and this is the zero vector. We're saying, well, if these vectors are linearly independent, then they're so dissimilar, they have no real relationship, that the only way that I can build a linear combination and get the zero vector out is if every single coefficient is zero, which of course that will work, right? But we would then say, okay, well then the set of vectors v sub 1 through v sub p is said to be linearly dependent if c sub 1 times vector v sub 1 plus c sub 2 times vector v sub 2 plus so on and so forth plus c sub p times vector v sub p equals the zero vector has a non-trivial solution. That is, there are some weights c sub 1, c sub 2, so on and so forth to c sub p where they are not all zero, such that my linear combination does in fact give me the zero vector. And we call such a case a linear dependence relation among those vectors. We have a nice theorem. An indexed set of vectors with two or more vectors where the first vector is not the zero vector is linearly dependent if and only if some vector in that set, some v sub j, where j is greater than 1, we said not the first vector, is a linear combination of the preceding vectors, where I can go ahead and write that vector as the preceding vectors with a bit of reordering. And we have a definition. Let H be a subspace of a vector space V, capital V, an index set of vectors, and we'll call that set beta with vectors b sub 1, b sub 2, so on and so forth, to b sub p, in vector space capital V, is a basis for H if we have the following two. Beta is a linearly independent set, and secondly, I need the subspace spanned by beta, the set, coincides with H. That is, my subspace H is equal to the span of those vectors, right? I need the span of my vectors from beta to coincide with H. Some more definitions, then we'll take a look at some ideas for the section. Let vectors e sub 1, e sub 2, so on and so forth to e sub n be the columns of an n by n identity matrix, capital I sub n, where little e sub 1 is the vector 1, 0, 0, so on and so forth, zeros all the way down. Vector e sub 2 is 0, 1, so on and so forth, zeros all the way down. And then, for example, if you want to jot another one down here, e sub 3, this would be the vector, the column vector 0, 0, 1, dot, 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 zeros all the way down. And then so on and so forth, e sub n is going to be the vector with zeros all the way down until the last entry is a 1. These are just, you think about the columns of the identity matrix, right? And here the set e sub 1, e sub 2, so on and so forth to e sub n is the standard basis for Rn. We're going to talk in the next section about working with non-standard bases, things like that. When we think of how we view most vector spaces, we think about it in terms of a standard basis. It's very natural, it's very easy to get around in a standard basis, but it is not the only way. But when you think about, for example, graphing in the xy plane, Cartesian coordinate system, you're thinking most likely of a standard basis, right? But we don't have to do that. We'll look at that in the next, not this one, the next one. We have the spanning set theorem. Let capital S be a set of vectors, v sub 1, v sub 2, so on and so forth to v sub p, be a set in vector space capital V, and let H be the span of those vectors, v sub 1, v sub 2, so on and so forth to v sub p. We have the following two comments to make. If one of the vectors in S let's call that vector some vector v sub k, is a linear combination of the remaining vectors in S, then the set formed from S by removing v sub k still spans H. So what we're saying is if I have some vector in there, and that vector is a linear combination of all of the other vectors, then I don't need it, because if I'm spanning the other vectors, then I'm going to get that vector somewhere along that journey. And secondly, if H does not equal the set containing only the 0 vector, so this is the 0 vector, but if H is not just the set with the 0 vector, then some subset of S is a basis for H. And then we have one more theorem, and then we'll take a look at what we want to talk about. The pivot columns of a matrix A form a basis for the column space of A. And we saw this previously. If I'm looking to form a basis for the column space of A, I need to find those pivot columns, and then we should be good to go. Take a look at an example. We're going to see a few of these. Determine whether the following sets, so we have one to start with, but we'll see others, whether the following sets are bases for R3. If the set is not a basis, determine if it is a linearly independent set or if it spans R3. And there's a lot of stuff to sort of talk about here. I'll try to be as descriptive as possible, and the wording might be a little bit confusing with how this is sort of phrased, but I'll do my best to explain what's going on. Let's take a look at this first set. So you have 3 vectors, and if you want, though, we can see that we have 3 vectors. We can put them in a set, the curly braces, separate the vectors with commas, however you like. But I have the vector 1, 1, 0, 0, 0, 0, and 0, 1, 1. And right away, we can actually answer this question. In order to have a basis must be a linearly independent set. Has to be. A basis must be a linearly independent set. But there's something to notice about the set that we have is that we have the 0 vector in the set. So we'll say any set containing the 0 vector is automatically a dependent set. So right away, I can answer the first question. This is not a basis for R3. Not a basis, because I have a dependent set. However, I still have a follow-up question, right? So I can already say it's not a basis. The set is not linearly independent. But I do want to answer, does it span R3? And depending on how much you already know about linear algebra, or if you're following along with our lecture material, you might have a good idea so far. But let's check. I'm going to take these vectors and use them as column vectors in a matrix, and I want to reduce. I want to find my pivot columns. The pivot columns are the linearly independent column vectors. So what can I do to reduce? Well, first I can do some row reduction. I can replace row 2 with row 2 minus row 1. So here I'm going to rewrite row 1. For row 2, I get 1 minus 1 gives me 0. 0 minus 0 gives me 0. And 1 minus 0 gives me 1. And I can rewrite row 3. And almost fully reduced, just one more step of row reduction to go, I can replace row 3 with row 3 minus row 2. So rewriting row 1, rewriting row 2, and then row 3, 0 minus 0 gives me 0, and then again, and 1 minus 1 gives me 0. So I can see this is fully reduced. And what I can do is I can actually spot my pivot entries. There they are, my pivot entries. And I can think about the columns that they live in. So column 1 and column 3 are my pivot columns, which means in my original matrix, columns 1 and 3 are my pivot columns. And we'll say the following. The pivot columns are the linearly independent columns. Which means that if I go back to my set, because that's how I built this matrix, is from the set, these vectors are the independent ones. If you want to sort of, the whole set is a dependent set. We already pointed out that the 0 vector is the problem, and the remaining vectors aren't multiples of each other. But it's interesting to sort of see that corroborated with our row reduction. But what can we say about this? Well, okay, so here what we have are these 2 column vectors. And I know it's not going to span R3. For it to span all of R3, I would need to have 3 pivot columns. So let's get a different color. Go back to the yellow. So we can say this will not span R3. And what we mean by that when we say this, it will not, so we'll say will not span all of R3, certainly not. But we can actually comment a bit further beyond this. This will give us a 2-dimensional, so this is, I feel this is very pessimistic. It's true, this is the truth, right? It's not going to span R3, no luck, no good. It's not going to span all of R3 anyways. But if I want to be sort of a glass half full kind of person, or a coffee mug half full of Starbucks kind of guy, then I can make some comment here. I can say what it will do. Let's be maybe optimistic about the situation. This will give us, let's say it gives us a 2-dimensional span of R3. Right, it's these 2 vectors that I have that are independent. Really, that 0 vector is ruining things for us anyways. It's not going to span all of R3, certainly not. But it will give us some 2-dimensional span of R3. I'm not going to be able to get everywhere in R3, but whatever lives in the span of that first and that third vector of the set, I can navigate freely there. Let's take a look at another example. Again, same question. I want to know, here's my set of vectors. Make it a set of vectors. I want to know, is this set going to be a basis for R3? Now, right away looking at it, I can't disqualify it immediately. It looks okay. I got 3 vectors, 3 entries each. So what do I have to do? Well, I have to go and do some row reduction. So write these columns in as columns of a matrix. You got it. And start reducing. Now right away, I'm going to do 1/2 row 1. I don't know if you're looking at that and thinking the same thing. I'm thinking 1, 1 minus 4. Just cutting everything in half. And then I can use that 1 in the upper left corner to get zeros underneath it. So I can replace row 2 with row 2 plus row 1. And I can replace row 3 with row 3 minus row 1. So let me rewrite row 1. Row 2's position, -1 plus 1 gives me that 0 that I wanted. -3 plus 1 gives me -2. 5 plus -4 is going to give me 1. And then in row 3's position, 1 minus 1 gives me 0 that I wanted. 2 minus 1 gives me 1. And 4 minus -4, that's 4 plus 4, gives me 8. And this looks good. I would probably want to do some row swapping, some row interchange. I'm going to put row 3 in row 2's position and vice versa. So leaving row 1 alone. But then in row 2's position, I'm going to have 0, 1, 8. In row 3's position, I'm going to put that row 0, -2, 1. And now I can work with some more row operations. So here, I'm going to use this. I'm going to try to get this in a triangular form first. Let me see if I can get rid of this -2, and then it should be easier to work from there. So if I want to get rid of this -2, that means I want to work in row 3 using row 2. And I can replace row 3 with row 3 plus 2 times row 2. So I'm going to rewrite rows 1 and 2. And then row 3's position, 0 plus 2 times 0 gives me 0. -2 plus 2 times 1 gives me that 0 that I wanted. And 1 plus 2 times 8, so that's 1 plus 16, gives me 17. And now I have this nice upper triangular matrix. But from here, I should be able to row reduce to a fully reduced row echelon form. I would scale this third row, so 1 over 17 times row 3. That gives me 0, 0, 1 for that third row. I can rewrite the rest. And now I can use row 3 to get zeros directly above, sort of completing that last column. So the rest of this row reduction, if I do it in sort of the particular way, it's going to go really nicely. So let me go row 2 replaced with row 2 minus 8 row 3. Row 1 replaced with row 1 plus 4 row 3. I'll rewrite row 3. I'm just going to get zeros here above that 1 in row 3. So I get 1 plus 4 times 0, and then again, keeps my 1s. Negative 4 plus 4 times 1 gives me that 0 that I wanted. 0 minus 8 times 0 keeps my 0. 1 minus 8 times 0 keeps my 1. 8 minus 8 times 1 gives me that 0 that I wanted. And now just one more clean operation in row 1. And this is going to look really nice when we're done with it. Replacing row 1 with row 1 minus row 2. 1 minus 0 gives me 1. 1 minus 1 gives me 0. 0 minus 0 gives me 0. And I can rewrite the rest of the rows. So this reduced perfectly to the identity matrix. And we can go back to the invertible matrix theorem to answer the question, in fact. But what we're noticing, if I want to do the same thing as before, I have these 3 pivot entries, all of the columns, right? Which means if I go back to my original matrix, all of these columns are pivot columns. So what do I have here? Well, I have 3 linearly independent vectors in R3. That's going to give me a basis, a complete basis for R3. So 3 linearly independent vectors in R3. And pay attention to the similarities here. I have 3 independent vectors in R3. This gives a complete basis for R3. And even if we think about sort of writing it out a bit more longhand, we'd say, well, this gives us a 3-dimensional span of R3, which is the entire space. So this is now saying, hey, I can go anywhere in R3 from these vectors. This is going to get me everything. So this is a basis. So this is a basis for R3. And this is as good as it gets. We talk about glass half full. This is the entire glass is full with Starbucks coffee. Yes. Okay, well, what about this set that we have here? What about this set that we have here? Stay with the baby blue. I got 2 vectors in R3. Right away, you're probably noticing, hey, how can that give me a complete basis? I can only at best get sort of a 2-dimensional subspace. Another thing worth pointing out is that since we only have 2 vectors, we should be able to determine by inspection if they're linearly independent or not. They would have to be multiples of each other otherwise. If they were dependent, they would have to be multiples. And here, if I multiply to sort of get the first entries working, if I multiply this first vector by -4, it'll work, but not for the next entry, not for the next entry, so then it must not be true. However, nothing is more satisfying or rewarding than row reduction, and I am here for you, so we're going to row reduce. But we already know the situation with this set, but let's do the row reduction anyways, so that I can get a sense of purpose. You can use that 1 in the upper left corner to get zeros underneath it, you better believe it. You can replace row 2 with row 2 minus 2 times row 1. You can replace row 3 with row 3 plus 4 times row 1. Let me rewrite row 1. 2 minus 2 times 1 gives me 0. 3 minus 2 times -4. Be careful with the double minus signs. That's going to be 3 plus 2 times 4, and that's 3 plus 8, which is going to give me 11. And then in row 3, -4 plus 4 times 1 gives me the 0 that I wanted. And then 6 plus 4 times -4, so that's 6 plus -16 is going to give me -10. Then I can scale rows 2 and 3. So we'll do 1 over 11 row 2. We'll do 1 over -10 row 3. So row 1 is going to stay the same, but rows 2 and 3 are both going to be 0, 1, and then 0, 1. And now I can do one more step of row replacement. I can go to row 3, replace with row 3 minus row 2. I can also go in row 1 and replace with row 1 plus 4 times row 2. So I'm going to rewrite row 2 right in the middle. In row 1, I get 1 plus 4 times 0 gives me 1. Negative 4 plus 4 times 1 gives me a 0 that I had wanted. And working in row 3, 0 minus 0, 1 minus 1 just gives me that row of all zeros. So like we said, right, these columns are linearly independent. So we can start to make a comment about this. So this is a linearly independent set and does give a basis for R3. Now, before you get angry and start yelling at me, I know what you're thinking. I'm going to clarify on this. And it all depends on what text you're working out of, what it is you're trying to convey. So you know I'm very verbose. You know I love to talk. I'm a chatty Cathy. I'm a fan of always saying more and getting my point across than leaving things open to interpretation. It is not going to give a complete basis. It's not going to get me everything in R3. But since it is a linearly independent set, and my set does span some of R3, it is going to be considered a basis for R3. But let me clarify on this in a way that hopefully will not leave a bad taste in anyone's mouth. It does give a basis, we'll say, for a subspace for R3. Or I guess it should be of R3, but whatever. It does give a basis for a subspace of R3. And this is going to give us a two-dimensional span of R3. And I can be very clear here. I can say this is not a complete basis for R3. I want to make sure that we're all on the same page. It's not a complete basis for R3. I can't get anywhere in R3. I can only get to whatever lies in the span of these two vectors, whatever is in this plane in R3 dictated by these two vectors. But it is going to give me a basis for a subspace of R3. So I'll write it again because I never get sick of writing it. This is a basis, not a complete one, but it is a basis for a subspace, a two-dimensional subspace of R3. I'll write that in. I like saying more. It's a basis for a two-dimensional subspace of R3, a plane in 3 space. Hey, what do we got here? We got another set of vectors. Who knew? Did you know? 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 Set of vectors. I hope you're thinking what I'm thinking, because if you are, then that means you've been paying attention to the previous lectures. I have how many vectors in R3? 1, 2, 3, 4. Let me know in the comment section below what you're thinking. Pause the video. Welcome back. We have too many vectors and not enough entries, so the set must be linearly dependent. Too many vectors. Too many vectors. Not enough entries. What's the best I can do? The best I can do is 3 independent vectors in R3. There's not going to be a 4th independent vector in R3. I can't get a 4th pivot column. It's not going to happen. Not mechanically, not theoretically. So right away, and we have this as a theorem earlier, right away I can spot this as an issue. At most, I can only have 3 independent vectors in R3. Fewer, sure. More than 3, no. Exactly 3, hey, that's good. More than 3, no. Less than 3, yeah. Exactly 3, that's my favorite. More than 3, no. So right away, I already know. I'm having a good time. Right away, I already know the story here is that the set must be linearly dependent, which is bad for a basis. A basis is never allowed to be a dependent set. And we're not allowed to just kick vectors out of a set. We can certainly find out which of these vectors is, the bad vector, or if there's a couple of bad vectors in there, we can find out, we can figure it out. but we can't go and start kicking it. We're not allowed to just, you know, kick them out of the set. We don't have that power. We don't have that jurisdiction. But the set we know has to be a linearly dependent set, right? So I'm not going to be able to evict anything out of the set, but I can tell you which ones should be if we had that chance, but we don't. So right away I know a set must be linearly dependent, so the set is not a basis, right? I'm not allowed to have a dependent set if I'm talking about a basis. So not a basis for R3. But the question remains, will this set span R3? And that is a different question. So when we say that, we say, well, it's not a basis for R3, so it's not going to be an efficient spanning of R3. It's not going to be the best possible spanning of R3. We did have an example. Let's scroll back up to it. This one, right? This one was beautiful. This one was perfect. 3 vectors in R3, all linearly independent, complete basis, beautiful. This right away, I know it's not a basis, but will it still span the entire space? Or a subspace? Let's see. Let's build a matrix. Take those column vectors, make them columns of a matrix. You know, you've already probably started writing this down on your loose leaf paper. I'm just trying to catch up to where you are. Let's reduce. I have a 1 in the upper left corner. You know how happy that makes me. I'm going to do some row replacement, replacing row 2 with row 2 plus 2 times row 1. And while we're at it, replacing row 3 with row 3 minus 3 times row 1. Let me rewrite row 1. In row 2's position, negative 2 plus 2 times 1 gives me that 0 that I needed. 3 plus 2 times 0 keeps my 3. Negative 1 plus 2 times 2, negative 1 plus 4 gives me another 3. And 0 plus 2 times 0 gives me 0 back. Let's go to row 3. Let's do this. 3 minus 3 times 1 gives me that 0 that I needed. Negative 1 minus 3 times 0 keeps my negative 1. 5 minus 3 times 2, that's 5 minus 6, gives me negative 1. And negative 1 minus 3 times 0 gives me negative 1. Looking pretty good. Let's do some scaling. What do you think about that? Let's go to row 2. We'll do 1/3 row 2. Go to row 3. We'll just flip the sign. Negative 1 times row 3. Let me rewrite row 1. Row 2's position, divide everything by 3. We get 0, 1, 1, 0. Row 3, flip the sign. 0, 1, 1, 1. And then I can replace row 3 with row 3 minus row 2. I mean, you knew I was going to do it. You wouldn't blame me. I'm only human. I'm not a robot. Bleep, bloop, bleep, bloop, bloop. 0 minus 0 gives me 0. 1 minus 1 gives me 0. And then again. And 1 minus 0 gives me 1. And I hate to say it, but it looks perfect to me. Looks like it is fully reduced. Let's get pink. I'm doing baby blue. Let's do the baby neon pink. Here I got pivot entry, pivot entry, pivot entry, and the columns look great in the reduced version. But I'm seeing here it's columns 1, 2, and not 3, 4. Columns 1, 2, and 4. So let me go back to the original matrix. We said 1, kind of cut it off there, but you get it. 2 and 4, which means that it looks like this third column vector is not independent. This is the one that I should be kicking out if I could. But I'm not allowed to kick vectors out of the set. The set's already been built. It's already here. You know, they're all friends. But if you want to point the finger and say, well, which one of these vectors isn't doing the work that they should be doing? Well, it's this vector right here. This is the bad one. But we do have these ones, vectors 1, 2, and 4, are linearly independent. And if they were in a different set without that third vector, then it would be nice. But we don't have that power. We can't just start kicking things out of sets. We don't get to play that game. But what can I say? We can say, although this set is not a basis for R3, let's give a shout out here in parentheses. We'll say linearly dependent set, sad face. we can say the following. It will still span R3 because I have 3 independent vectors in that set in R3. So it will give a 3-dimensional span of R3. It will still span all of R3, but in order to be a basis, there are some technicalities to consider, right? Although it can get me anywhere in R3, it will not be allowed to be a basis because it's not allowed to be a dependent set, and it messed that up at the very beginning. But it's trying to do its best. It's still going to span R3. It's trying to make up for its mistakes. But it'll never be a basis. Never. Not ever. Hey, let's talk about some of our favorite bases. Let's find a basis for the null space of the given matrix. And you know what we like to do here. We like to take this matrix and augment with the 0 vector. Let me just pretend like I'm augmenting with the 0 vector and pretend like this little line isn't here. And then let's start row reducing. Let's start row reducing. So what I'm going to do, I'm going to rewrite the first row. We're augmenting this with the 0 vector, so it looks a little better now. I'm going to rewrite the second row, augmenting with that 0 vector. Now I'm going to do some row replacement here in this third row. So I'm going to use this 1 in the upper left corner. I'm going to try to get rid of that 3. I'm going to replace row 3 with row 3 minus 3 times row 1. So what's that going to give me? 3 minus 3 times 1 gives me that 0 that I wanted. Negative 1 minus 3 times 0 keeps my negative 1. Negative 7 minus 3 times negative 2, careful with those double minus signs, that is negative 7 plus 6 gives me negative 1. And then 3 minus 3 times negative 2, again the double minus signs, that's going to be 3 plus 3 times 2, that's 3 plus 6 gives me 9. And then 0 minus 3 times 0 gives me 0 in the augmented entry. Now I can do some more row replacement. I can replace row 3 with row 3 plus row 2. Seems reasonable to do that, so let me rewrite the rest. A lot of rewriting matrices. I think it's very therapeutic, nice and calming. Now we get to the action. 0 plus 0 gives me 0, negative 1 plus 1 gives me 0, and then again, 9 plus 4 gives me 13. 0 plus 0 gives me 0 in the augmented entry. Now from here, the rest of the row reduction is going to go quickly. I can scale row 3. We'll do a 1 over 13 times row 3. We rewrite rows 1 and 2. And then dividing everything in row 3 by 13, we get 0, 0, 0, 1, augmented with 0. Now columns 1 and 2 look great. Column 4, I'm going to clean up here in my coefficient matrix. I can very safely and surgically get a 0 where that 4 is and a 0 where that negative 2 is, right above that 1 in the third row. What are the operations? I'm going to replace row 1 with row 1 plus 2 times row 3. I'm going to replace row 2 with row 2 minus 4 times row 3. Let me rewrite row 3 to start. And in row 1, sure, 1 plus 2 times 0 keeps my 1. 0 plus 2 times 0 gives me 0 back. Negative 2 plus 2 times 0 keeps my negative 2. And then negative 2 plus 2 times 1 gives me that 0 that I wanted. And then any operation on zeros, any linear operation on zeros keeps my zeros where they are. So as promised, very surgically got that 0 where I wanted it. In row 2's position, 0 minus 4 times 0 gives me 0. 1 minus 4 times 0 keeps my 1, and then again. 4 minus 4 times 1, though, gives me that 0 that I wanted. And then I keep my 0 in the augmented entry. Now this is fully reduced. Fully reduced. And I can use this to help me build a basis for my null space. So we'll say, well, looking at this, I have pivot column in column 1, pivot column in column 2, and then pivot column in column 4, which means my free variable comes from column 3, and that's where x sub 3 lives, right? x1, x2, x3, x4. So x3 is my free variable. And let's write out what these equations are trying to say. This first row is saying x1 minus 2x3 equals 0. Second row, is saying x2 plus x3 equals 0. And the third row is saying x4 equals 0. And we want to mention, x3 is free as well. So let's go ahead and solve these, right? x1 equals 2x3, x2 equals negative x3, x3 is itself, and x4 is equal to 0, or you could think of it like a 0x3. So when I go to write my vector, x, I can write it in terms of the free variable. So the first entry, x1, can be replaced with 2 times x sub 3. The second entry, x sub 2, is really negative 1 times x sub 3. The third entry is x sub 3 itself, and this is my free variable, so I want to keep it alive. That is 1x3, it is itself. And x4 is just supposed to be 0, so the best we can write it as is 0x3. And then I can bring x3 out as a scalar weight, and I'm left behind with this numerical vector 2, negative 1, 1, 0. And this is going to be my basis for the null space. So basis for the null space of A for that given matrix is set with, it just has one vector in it. I just had the one free variable. It's the vector 2, minus 1, 1, 0. That's it. It's my basis for the null space of A. And I haven't really named this matrix A yet, but you can name it A now if you want to, this matrix here. Another familiar example, assume that matrix A is row equivalent to matrix B. Find bases for the null space of A and the column space of A. Now, we know what to do, right? So to find a basis for the column space, it's the pivot columns. And we're going to go into this already pre-reduced version and find the pivot entries and the pivot columns. So in row 1, bam, right away, pivot column, column 1. So I'll make a little mark there. Go through row 2, pass through the zeros, bam, there's my pivot entry, this 3 right at the beginning. And then here it's this third column then, which must be a pivot column. And then go through row 3, pass through the zeros, right at the end, this negative 7 is my pivot entry, and that is in column 5, the last column is a pivot column. And this last row of all zeros, we pass through like ghosts in the night. Let me know in the comment section below if you believe in ghosts and the paranormal. And if you don't, let me know that you don't, but let me know if you believe in linear algebra. Let's take a look at what we can do. So since this has already been reduced, and if I didn't have this reduced version, I would just find the reduced echelon, the fully reduced row echelon form of this matrix myself, but this speeds it up for us a bit because we spend a lot of time row reducing together. So always nice when we can get a situation like this. But I would do this, I would find those pivot columns, and I have to take the column vectors from the original matrix, always the original matrix. But I can do this now. I can say a basis for the column space of A is, now it's going to be a set. It's going to have 1, 2, 3 vectors in it. So I like to do the 3 empty boxes. Separate with commas. And it's going to be columns 1, 3, and 5. So the first vector is 1, 1, 2, 3. And then the second column vector, 3, 0, negative 3, 0. And then it's this last column vector, 8, 8, 9, 9. Which means that these other two columns, I must be able to write these as a linear combination of the other 3 columns. Kind of cool to think about that. So we already have the basis for the column space of A. Always take that from the original matrix. Now to build the basis for the null space of A, I have to reduce. Further. So that means whoever was reducing this matrix didn't quite finish that part of it, but let's go ahead and take a look at it. So now I'll say, well, for the null space of A, what I could do is I could actually scale rows 2 and 3. I would like to do that. And I'm going to augment with the 0 vector. Of course I am. So for row 2, I'm going to do 1/3 row 2. For row 3, I'm going to do negative 1/7 row 3. Let me rewrite row 1. That's 1, 2, 0, 2, 5, and then augmented with 0. Row 2, if I divide everything by 3, I'm going to get 0, 0, 1, negative 2, 1, augmented with 0. In row 3, if I divide everything by -7, I'm going to get 0, 0, 0, 0, 1, and then I'm augmenting with the 0 vector. And that last row is just a row of all zeros, and I'm now augmenting with 0. And let's go through some row reduction. Now this row 3 is already set up perfectly to get zeros very safely, very surgically right above it. So I'm going to take that opportunity and make the most of it. I'm going to work in row 1, replacing row 1 with row 1 minus 5 times row 3. I'm going to work in row 2, replacing row 2 with row 2 minus row 3. And I'm going to rewrite row 3, 0, 0, 0, 0, 1, augmented with 0. And I'm going to rewrite row 4, which is just that row of all zeros and now augmented with 0. But in row 1, you can see I'm going to get a lot of 1 minus 5 times 0 and 2 minus 5 times 0, 0 minus 5. This is going to keep those entries. I'm just going to be subtracting 0 away until I get to this last entry of the coefficient matrix, 5 minus 5 times 1. Now that's something we can talk about. 5 minus 5 times 1 gives me that 0 that I wanted. And then 0 minus 5 times 0 gives me 0 in the augmented entry. Now similarly in row 2, I'm going to see a lot of no movement, right? 0 minus 0, 1 minus 0. It's going to keep those entries, -2 minus 0, but then 1 minus 1 is going to give me that 0 that I wanted. So very safely and surgically, this has worked out nicely. And it looks like we're fully reduced now, right? Look at those pivot columns. They look beautiful. Zeros above and beneath the leading ones. This is fully reduced. What are the free variables? Let's get purple in here. So we already said pivot columns 1, 3, and 5. That's where my basic variable lives, which means I have a free variable in columns 2 and 4, which means x2 and x4 are the free variables. Let's see what happens next. Let me write out these equations that the rows are saying. So the first row says x1 plus 2x2 plus 2x4 is equal to 0. Second row is saying x3 minus 2x4 is equal to 0. And the third row is saying nothing until it gets to x5 equals 0. And worth mentioning that x2 and x4 are free. So when I go to write these out as vectors, we'll say, well, x is equal to, I can get two vectors set up here, one relying on x2, one relying on x4. And we'll say, well, x1, if I were to solve this, so I sort of skipped over the step here, but move it to the other side. x1 is a -2x2, and then a -2x4. The second spot is for x2, and that is my free variable. So that's 1x2, 0x4. Now for x3, x3 is going to be equal to +2x4. I move that over, and that would mean 0x2 then, because it's missing. The next spot is for x4. So that's going to be 0x2 and then 1x4. And then x5, my fifth spot, is supposed to be 0. So that's got to be 0x2 plus 0x4. And now I can bring out x2 and x4 as scalar weights. Oh, we got good news for everybody is that Spumoni's here to help. Have you seen my cat Spumoni? She's here to help us build our basis for the null space. What do you think, Spumoni? What was that? Gotta say it into the microphone. Spumoni wishes you luck in building bases for column space and null space. Spumoni, wish them luck. You got this, she says. You guys got this. Little cute little cat. Let me know in the comment section below if you think Spumoni is a cute cat. You gonna help? We're almost done. So you came at a really good time. You weren't even, like, there were trickier parts in the beginning. I was stuck before, but I got through it without your help, and now you're showing up, and you're like, well, let me help you now. It's like, well, we're already done. We're already done. We're practically already done. All right. All the same, thank you. Under her careful aegis, we can finish the problem now. Bring out that free weight x2. We're left behind with numerical vector -2, 1, 0, 0, 0. Bring out x4. We're left with numerical vector -2, 0, 2, 1, 0. And it is those numerical vectors that are going to build our basis for the null space of A, right? Think of this as a plane in R5, right? 1, 2, 3, 4, 5 entries in these vectors. And how does it get its shape? Well, we pick whatever we want for the free variables. The shape is dictated by these two vectors. So basis for the null space of A, you know what it's going to be? It's going to be a set. In that set, there's going to be two vectors. They got to be separated with a comma. And it's going to be the vector -2, 1, 0, 0, 0, and the vector -2, 0, 2, 1, 0. And we got our basis for the null space of A. Fantastic. Going to take a look at just a couple more questions, and then we're going to have to boogie on out of here. I want to find a basis for the space spanned by the given vectors. And here I have all these vectors given. 1, 2, 3, 4, 5 vectors in R4. And we know right away, too many vectors, not enough entries. So we already know that the set is not independent. But if I want a basis for the space spanned by these vectors, what we want to do is we want to find out which of these vectors are the linearly dependent vectors. Kick them out. Kick them out. So really think of it like building a basis for column space if you want to connect it to that. So let's take these vectors, throw them into a matrix. So write the columns in as column vectors. We've gotten a lot of practice doing this. Someone's like literally right here still, hanging out with me. But let's do this. Let's do the reduction. So I have this 1 in the upper left corner. I'm going to use that to get zeros underneath it, but I already have a lot of them. So I'm going to work in row 4, replacing with row 4 minus row 1. And I can't resist, right? I see you, row 2 and row 3. You're just waiting for me to do some row operation. I'm going to go to row, it doesn't matter, but I'm going to go to row 2 and replace row 2 with row 2 plus row 3. Why not? So I'm going to rewrite row 1. Just rewriting it. Row 2, I'm going to replace it. 0 plus 0 gives me 0. And then again, -1 plus 1 gives me 0. -3 plus 3 gives me 0. -1 plus 1 gives me 0. So hey, that will see you later. Row 3, I'm going to rewrite that. 0, 0, 1, 3, 1. Row 4, now I got to do some work, right? 1 minus 1 gives me that 0 that I wanted. 2 minus -2 gives me 2 plus 2, which is going to give me 4. -1 minus 3 is going to give me -4. -4 minus 5 is going to give me -9. And 0 minus 2 is going to give me -2. So it looks good so far. What I'm going to do then is I'm going to do a row interchange. I'm going to swap rows 2 and 4. I'm going to put row 4 in row 2's position, row 2 in row 4's position. So rewriting row 1. And then my row 2 is now going to be 0, 4, -4, -9, -2. Row 3 is still going to be my 0, 0, 1, 3, 1. And then row 4 is going to be that row of all zeros. Should be at the bottom anyways, right? Now let's see, where can I go from here? Well, now what I could do is I could go ahead and it depends on what you sort of want to work with first. I might be inclined to, for example, use this leading 1 in row 3 to try to get a 0 in row 2. At some point, I'm going to have to address pitting rows 2 and 1 against each other. Let me just pick and choose how I'm going to do this. I'm going to replace row 1 with row 1 minus 3 times row 3. That's 1 minus 3 times 0 gives me 1. -2 minus 3 times 0 gives me -2. 3 minus 3 times 1 gives me that 0 that I'm going to need. And then 5 minus 3 times 3, so that's 5 minus 9 gives me -4. And 2 minus 3 times 1, 2 minus 3 gives me -1. So not so bad so far. And then, if I'd like to, what I could do is I could replace row 2 similarly with row 2 plus 4 times row 3. So 0 plus 4 times 0 gives me 0. 4 plus 4 times 0 gives me 4 back. Negative 4 plus 4 times 1 gives me that 0 that I wanted. Negative 9 plus 4 times 3, that's negative 9 plus 12, gives me positive 3. And negative 2 plus 4 times 1, negative 2 plus 4 gives me positive 2. And I can rewrite row 3. I can rewrite row 4. Now, row 3, sorry, column 3, I used row 3 for these operations. Column 3 looks perfect. But I am going to have to now do some work between rows 1 and 2. And let me just take this time then to actually, I'm going to scale up row 1. I like to avoid fractions, you know that about me. So I'm going to do 2 times row 1. And that's going to give me 2, negative 4, 0, negative 8, negative 2. I'm going to rewrite row 2. I'm going to rewrite the rest, right? I'm going to rewrite everything else. So row 3 I'm going to rewrite as well. And I'm going to rewrite row 4, row of all zeros. But now I can do some row operations, and then I'm going to scale, right? So I'm going to go to row 1 and replace with row 1 plus row 2. So 2 plus 0 gives me 2, negative 4 plus 4 gives me 0 that I wanted. 0 plus 0 gives me 0, negative 8 plus 3 gives me negative 5, negative 2 plus 2 gives me 0. And I can rewrite row 2. I can rewrite row 3. I can rewrite row 4, my row of all zeros. Now, if I'm looking at my pivot columns, I can see that they look good. Third column looks great. Columns 1 and 2 just need to be scaled. And then otherwise, I should be done. I should have my fully reduced row echelon form. We do have an answer when we find the pivot entries and the associated pivot columns, but always do the fully reduced row echelon form. Right? That's what we're here to do. So let me go ahead and scale. We'll do a 1/2 row 1. We'll have to do a 1/4 row 2. And row 3 I'm going to rewrite because that's fine. 0, 0, 1, 3, 1. Row 4 is just a row of all zeros. I'm going to rewrite that. But scaling row 1, dividing everything by 2, I'm going to get 1, 0, 0. I'm going to get negative 5/2, 0. And in row 2, dividing everything by 4, I'm going to get 0, 1, 0, 3/4, and then 2 over 4, which was going to reduce to 1/2. So fully reduced. I want to get that fully reduced matrix. Let's see what we got. Purple. Let's find the pivot entries. And then nothing in that nothing in that 4th row. But here I have columns 1, 2, and 3 are the pivot columns, which means that in my original matrix, columns 1, 2, and 3 are the independent columns, which means that in my set, since I didn't change the order around or nothing, vectors 1, 2, and 3 are the independent vectors, which means, hey, this 4th vector, this 5th vector, they must already be a linear combination of these 3 vectors. So I don't need them. If I think about spanning all of these vectors, if this vector is already a linear combination of these 3, and if this 5th vector is also a linear combination of these 3, then if I just span these first 3 vectors, I'm going to get these other 2 vectors anyways in the span. These are redundant. I don't need them. So if I want a basis for the space spanned by the given vectors, we'll say a basis for the space spanned by the given vectors is, now it's going to be a set. There's going to be 1, 2, 3 vectors in the set, separated by commas. What are those vectors going to be? We have 1, 0, 0, 1. And the next one was negative 2, 0, 0, 2. I peeked at it. Negative 2, 0, 0, 2. And 3, negative 1, 1, negative 1. And that's going to be my basis for the space spanned by the set of vectors. I didn't need all of them, and in fact 2 of them I didn't need. So then I can go ahead and build my basis from those 3 independent vectors. Looks great. One last question that I just want to talk with you about, and this one's actually going to be, I think, a quick argument, a fun argument for us to make. Here I have 3 vectors, v1, v2, v3. Let H be the span of these 3 vectors. Now, I'm telling you that it can be verified that 4 times vector v1 plus 5 times vector v2 minus 3 times vector v3 is equal to the 0 vector. And you could do the arithmetic to show that, the vector arithmetic. I want to use this information to find a basis for H, where H is the span of these vectors. Now I want you to notice that the set then is a linearly dependent set. If I think about the set of these 3 vectors, it's a dependent set. And I have this non-trivial linear combination given to me. So what could I do? Well, think about it this way. What if I solve for vector v3? So we'll say 4 times vector v1 plus 5 times vector v2 is equal to, if I add this over, is equal to 3 times vector v3. And then what I can do then, let me write this on the other side and then divide by 3. That means vector v3 is equal to 4/3 vector v1 plus 5/3 vector v2. So what this means is I don't need vector v3 in the set, but I don't need v3 in the spanning set. Because if I'm allowed to multiply v1 and v2 and add multiples together however I'd like, well, there's a combination of v1 and v2 that's going to yield vector v3. So I don't need v3. v3 is already in the span of v1 and v2. So if I want to find a basis, so we'll say a basis for H could be just the set containing vectors v1 and v2. Make these look less like check marks. I want them to, oh, well, you know what? You're worth it. I don't want them to look like check marks. I don't want them to look like W's. I know it's my handwriting, so I'm not blaming you. v1, v2, and then the 2 is messed up now, but who cares? But that's not the only consideration, right? So another thing I could have done is I could have eliminated v2, right? What if I solved for v2? So we'll say, well, what about 4 times v1 minus 3 times v3 is equal to negative 5 times v2 if I swing that term over. And then I could solve for v2 and say, well, v2 then is equal to negative 4/5 v1, I'm dividing by negative 5, and then plus 3/5 v3. So then v2 is a combination of v1 and v3. So I would say, well, I could just have, so a basis for H could be just the set containing vectors v1 and v3, and I think you know where I'm going next with this, is that I could have eliminated vector v1 just the same. So let's say, what if I move that one over? So 5v2 minus 3v3 equals negative 4v1, right? If I move this one over, then I could solve for vector v1 as a combination of v2 and v3. So v1 is equal to negative 5/4 v2 plus 3/4 v3. So then v1 can be achieved as a linear combination of v2 and v3. So v1 lives in the span of v2 and v3. So a basis for H could be the set containing vectors v2 and v3. So there's 2 possibilities. Or sorry, 3. Sorry, I just made 3 of them. There's 3 possibilities. I don't need all of these vectors. I just need 2 of them. I don't need all 3 of them. So possible basis for H, question mark. We have 3 potential bases. Bases is plural, basis is singular. So we have 3 options. Could be the set containing vectors v1 and v2, or the set containing vectors v1 and v3, or could be the set containing vectors v2 and v3. Right? I don't need all 3 of them because they have that nice linear combination. Hey, Hope you've enjoyed it. If you've made it this far, let me know in the comment section below if you enjoyed this content. Otherwise, no matter where you are and what you're doing, make sure that you keep learning, keep dreaming, and always follow your heart. You know what? We'll be back at it doing more math with Kat. Spumoni's going to help us out again next time. Just being a good friend, good math helper. But hey, until then, take care of yourself, and I will see you next time.